So today I want to ask the question, what is the transpose of a matrix? So you should tell me, what's the transpose of a matrix? It's like, yeah, you switch the rows to the columns. It's like, yeah, that's what you do, but what is it? Right? Like, what is this creature? So like, if I ask you what the determinant of a matrix is, you're like, well, here's the way to calculate it, but we also have what it represents, right? Like, the determinant, if you think about a matrix as being a map from, say, Rn to Rn, what is the determinant telling you? Yeah, it tells you how much it scales by the change in volume. If you take some orthonormal basis, the determinant tells you how the volume changes of some like little cube or whatever it is that is spanned by original basis, how the volume of that changes. So like that's what a determinant tells you. How about the inverse of a matrix? Well, that's just a map going the opposite direction, right? A multiplication of matrices is just composition of maps. So it's like, what is the transpose of a matrix all about? It's like, well, if I think about a matrix as being a map, I can't really think of what the transpose has to do with that map. Suppose, let's think about some map A. Let's make this a M by N matrix. And let's say it's real values. So that means it's going to be a map from where to where? Well, if it's M by N, so if it's like 2 by 3, it eats in 3-dimensional things and then spits out 2-dimensional things, right? So a 2 by 3 is actually a map from 3 to 2. So an M by N is a map from Rn to Rm. And it's like, well, where is there any story involving the transpose? And it's maybe not obvious, but we've already seen this, that the transpose is related to the dot product. In particular, if I take something like AV dot W, that's going to be the same thing as just AV transpose W. We can continue to unpack this. AV transpose W is saying the same thing as just V transpose A transpose W. But then that's the same thing as V transpose would be just V dot A transpose W. So here it is algebraically. If you want to move a matrix from one side of a dot product to the other, it changes from A to A transpose. Yeah. Let's go ahead and think about what's going on here. Let's say V, let me get some colors. Let's say V is something here in my first vector space. So then AV is wherever that gets mapped to. So I don't know what AV is, but AV will be the image of your V. I don't know, maybe it's something like this. Here's my AV. And W is something over here. W is something over here. V lives in my first vector space. Where does A transpose V live? Well, let's think about A transpose. If A is an M by N matrix, then A transpose will be a N by M. Hence, though you can think of as a map, it's not an inverse map. This doesn't have an inverse. It's not a square matrix. But you can think of it as a map from Rm to Rn, because now it's an N by M matrix, right? So A transpose W is going to live back over here. It's like, what does it look like? I don't know. I don't know what it looks like, but maybe it looks something like this. A transpose W. Right? So we're saying that dotting these vectors in this vector space is the same as dotting these vectors in this vector space, where if you're going to move a matrix to the other one, you're changing it from A to A transpose. Right? So there's one way to think about what the transpose is. It doesn't just have to do with your map, but it also has to do with your dot product. And it's just thinking about how your map and your dot product play together. And it's telling you if you move from one side to the other side, that it's going to be taking the transpose. Well, in this course, we're not just thinking about vector spaces like Rn, but we're thinking about arbitrary vector spaces. So let's try and extend this definition to arbitrary vector spaces. Arbitrary vector spaces that have something like a dot product, which we'll call an inner product. So let's say we're given two inner product spaces. We're given some inner product spaces V and W. And in here, I'm assuming they have the same inner product, right? So I have some inner product spaces V and W. Actually, I guess you don't need them to be the same. But we have two inner product spaces V and W, and a linear transformation, and a linear transformation. T, which is some map from V to W. So here our transformation T is a more general form of, it could be like a matrix or whatever it might be. It's analogous to our matrix here, going from V to W. Then I'm going to call it adjoint of T is a linear transformation that should be going the opposite direction. And so we're going to instead have it a map from W to V, and I'm going to denote this by T star, such that you can move from one side of your inner product, for us inner product, to the other side by moving your linear transformation to its adjoint, such that TV inner product with W is equal to V's inner product with TW for all V and V and W in W. This should be the adjoint, T star. So take a second to understand what's going on here. W is in W, V was in V, but when you apply the linear transformation to it, okay, maybe I should put parentheses around this. When I apply the linear transformation to it, now these are both in W. These are two vectors in W. W is an inner product space, so I can take the inner product. And over here, V is in V. W was in W, but I applied T star to it. So now W is also in V, so these are two vectors in my vector space V. And since your vector space V is actually an inner product space, there's some inner product that you can calculate. Now, as long as these both are giving you the same kind of thing out, like both giving you real numbers, as long as these are both over the same field, then this makes sense. It's well defined. Okay. So we've already seen an example of this. The first example is just a matrix. The adjoint of a matrix is its transpose, right? What if our matrix is over, so this is over the real numbers. What if our matrix is instead complex valued? Then what will be the adjoint of a matrix? Conjugate transpose. Yeah, if you remember over the complex numbers, our dot product's defined a little bit different. AV.W isn't just AV transpose, but we define it to be AV conjugate transpose, which, by the way, we've been using the same symbol for. So there's a reason we're going to use the same symbol. It's because when you're working over complex numbers, the conjugate transpose is going to be your adjoint. So this just comes out to be here, and then by the exact same argument, you end up with V dot A conjugate transpose W. So the adjoint of a complex matrix is its conjugate transpose. The adjoint of a real matrix is its transpose. Good? Okay, so those are the two basic examples you should keep in mind. But it's like, this is over any vector space. And so what I want us to do is take a minute to think about, well, can we get a better handle of what's going on here over some arbitrary vector spaces? So let's say we have some vector spaces V and W. Well, that's about all I can say if all I know is that these are just arbitrary vector spaces. But if these are finite dimensional vector spaces, in particular, if this has some basis B with some, so this has some basis B, I don't know what that basis is, some V1 through, let's say maybe Vm, and this has some basis C. Let me do n here so it's just consistent with this previous picture we drew. That has some vectors W1 through Wm. Then, a game we've been playing quite a bit in this class is how do we get a handle on this linear transformation between vector spaces? Well, we think about mapping these vector spaces down by the coordinate map. So you just take any vector and you ask, what is that vector's in terms of its coordinates with basis B? And write the coordinates of that vector with respect to basis C. Right? Any vector in V is some linear combination of its basis. So it's one copy of the first guy, 3 copies of the next, or whatever. And so you'll map it down to the vector 1, 3, whatever. So this is mapping you down to Fn. F could be the real numbers, the complex numbers, whatever your field is. And this is mapping you down to Fm. And then we've already seen that given any linear transformation between vector spaces, there exists some corresponding matrix, right? Which I just denote by the matrix, although this matrix is dependent upon your choice of basis. So that's in basis B and sends you to things in basis C, right? Okay. So we can find the matrix corresponding to a linear transformation. Now, if I have this adjoint guy, if I have my T star, you can tell the exact same story. So there's going to be some matrix down here, which is the matrix that corresponds to your adjoint in terms of basis C into things in terms of basis B. And what I want to think about is how are these two matrices related? Well, do you have a guess? Right, it's like this is kind of the game we've been playing all semester. Is like, well, we know how it works for real and complex numbers, and we're going to say whenever you think about it up here and you map it down to just a map between Rn and Rm or Cn and Cm, it should work the same way. So what we want to show is that this guy down here, this matrix, is secretly just the conjugate transpose of the guy on top, right? So let me go ahead and write the result, and then we're going to prove it. So here's going to be our big theorem. Again, V and W are inner product spaces. And we're given a linear transformation, a linear transformation T from V to W, then what I want to argue is that there exists a unique linear transformation T star from W to V such that T of V inner product W is V T star W. So that is, there exists a unique adjoint. This is just saying it's the adjoint, where the matrix corresponding to T star, where that is a matrix from some basis C to B, will just be equal to the conjugate transpose of the matrix from B to C. Okay, I'm going to add a couple more adjectives here in a second. That's almost true. We need one more tool in a second. But that's the idea. I want to say that given any linear transformation, there exists an adjoint. And what is the adjoint? Well, it's just the thing whose matrix is the conjugate transpose of the matrix of the other guy. Right? So that's what we're trying to say. And it's unique. There's a unique guy corresponding to the unique matrix here. So why should we believe this? Right? How should we begin to think about this? Well, let's go ahead and say we have some V in V and some W in W. Then I can think about my inner products. So in particular, over here, I'm going to have the inner product of TV with W. And over here, I'm going to have the inner product of V with the adjoint of T, W. But we've already said, if we pick our basis well, if we pick B and C to be not just any basis, but we pick these to be orthonormal, basis, then an inner product is the same thing as what? When working over an orthonormal basis, this can be expressed as just this is one of our big results from a couple classes ago. Do you remember? It's like, this is why it's nice to pick orthonormal basis. Because then our inner product is just our, what is inner product generalizing? It's generalizing dot product. And if you pick an orthonormal basis, this is going to be the same thing as just T of V expressed in that basis dot W expressed in that basis. Do you remember that? And over here we have the same thing. If we pick our basis to be an orthonormal basis, this inner product is going to be the same thing as just V expressed in that basis times the adjoint acting on W expressed in that basis. But then we can go back even further. It's kind of a review of everything we've done so far. What is the vector that corresponds to a linear transformation acting on V expressed in this basis? Well, that's going to be the same thing as the T matrix acting on the vector V. expressed in this basis, where T is some matrix that's going from basis B to basis C, and V is living in basis B. And so it's really this guy that's getting dotted with W. And in the exact same way, over here, you just have V is being dotted with, well, this is just going to be the matrix corresponding to T star times the vector W, where W is inside the basis C, and T star is some matrix that's moving from basis C to basis B. And then you're like, well, dot product is just multiplication by, if we're working over complex numbers, conjugate transpose. So this is really just VB conjugate transpose, T conjugate transpose, B to C, times W. And over here, we have B conjugate transpose times the matrix for T's adjoint times W. But finally, we said the definition of adjoint is that this guy up here is equal to this guy over here. These are equal to each other. This, okay, these are equal. Bam. These equal, right? Very long equality. Which means this guy on the bottom is equal to this guy on bottom for all V in V and W in W. Okay, so I think we're almost there now, but let's just convince ourselves that we really have proven it. I was trying to show that this matrix right here is the same as this matrix right here. Well, we almost have that. There's some extra stuff on the sides. We'll talk about that in a second. But note one important piece. This argument only works if our basis B and C are orthonormal basis. So let me include that in my theorem, where these matrices are equal to each other, and your B and your C are your orthonormal bases for V and W respectively. So I want to show these matrices equal to each other, but let's see what we've actually shown. So I'll just note here, let me come over here. So far, we have that V expressed in the basis B, conjugate transpose, times the adjoint of T, expressed as a matrix, times W's coordinate vector in C is equal to V, B, conjugate transpose, the matrix corresponding to T, conjugate transpose, times W. For all V and W. So how can we show that these matrices are actually equal? Well, here's what we're going to do. Let's pick, in particular, let's pick your V to be equal to, say, your ith basis element, and your W to be your jth basis element. So then you tell me, what will be Vi written as some vector in terms of basis B? Well, it's already an element of basis B. It's just the ith element. So what guy is this? What does this vector look like? Yeah, it's all zeros, but there's a 1 in the ith position. There's a 1 in the ith position. And so I'm just going to refer to that as EI, the elementary vector that has a 1 in the ith position. And exactly analogously, what is WJ written in terms of your basis vector for C, your basis C? Well, it's already the jth element of the basis for C, so that's just going to have 1 in the jth position, so that's just EJ, which just means it just has a 1 in the jth position and i's everywhere else. So then, what does this become? If we plug in these particular values for V and W, here we get the EI conjugate transpose times this matrix times EJ is equal to EI conjugate transpose times some matrix times EJ. So like, take a second to think, like, what goes on with this multiplication? Here I have some matrix. I don't know what the matrix is. Say it's some like 3 by 3 matrix. Say you have some like 3 by 3 matrix. And on one side, you have something in EJ. I don't know what it is. Maybe it has 1 in like the second position. What is that multiplication going to do? Yeah, it's just going to kill everything, giving you the second column. Or in particular, that multiplication gives you the jth column. It's just going to give you the jth column. Right? And then on the left, you're multiplying by this guy that has a 1 in the ith position. Like maybe it's the first position or something. What happens if you multiply the jth column of this? So now you just have the jth column. Now it's just the jth column. I don't know what that jth column is, but it's just the jth column. Times this. What are you going to get returned? The first element of the jth column, or the ith element of the jth column. Right? So in general, this is just going to give you, so then this gives you the I jth element of whatever your matrix was. So what this is saying is it's saying the I jth element of this matrix has to be equal to the I jth element of this matrix. Right? So this is saying it has the same, these matrices have the same I jth element. But this is true for any V and V or W and W. So just take all combinations of VI and VJ, and then you conclude that these two matrices have all the same elements. And since they have all the same elements, therefore we can conclude, like thus, we've shown that these matrices are actually the same. The conjugate transpose of T is the same as the matrix which is the matrix for the adjoint. So how do you find the matrix for the adjoint? You just take the conjugate transpose of your original matrix. So let me make sure I get my bases right. This guy is going from B to C, and this guy was going from C to B. Which is what the theorem is saying. Okay. Well, you should convince yourself that we actually did prove it. So I'm saying the adjoint always exists. Why does the adjoint always exist? Well, if these are finite dimensional, you can represent T by some matrix. Then you just take its conjugate transpose. You'll get this matrix. And once you have this matrix, you can ask what's the linear transformation that corresponds to that matrix, and that will be your adjoint. Right? So that gives you existence. Why is it unique? Well, because at all these steps we had uniqueness by our previous theorems. That, given a linear transformation, there exists a unique matrix. It's the uniqueness from previous theorems that gives us uniqueness here. I mean, the elements here, all the elements are just forced to be these elements, right? So you're guaranteed to have uniqueness. Okay. So now we have existence and uniqueness of an adjoint for finite dimensional vector spaces. So I think the way we should wrap up class today is for me to give you an example, right? So let's go ahead. Like I've shown you these things exist, but what do they look like? So let's go ahead and take a vector space, not Rm or Rn, but something very different looking, and some linear transformation on it. So let's do one we already did a couple of weeks ago, maybe a week ago, I don't know, whenever the last time we did this. We are thinking about the vector spaces P1 and P1. So this is polynomials up to degree 1, right? So things of the form a plus bx. And we're thinking of some map between here. And let's say these are like over the real numbers, just for simplicity. And so what's a nice linear transformation that takes a polynomial and gives a polynomial? Well, let's do the derivative. Right. So I want to find the adjoint of the derivative map. You all ready for this? Okay. So the way the story works is it says we can think about P1 and P1 as being two-dimensional real vector spaces. So there are maps down here. And there should be some corresponding matrix down here that corresponds to the matrix that corresponds to D. Right? Okay, so what is this matrix? Well, first, what is our basis? What is our basis for this guy? You attempted, I mean, it's the same basis for both of them, and you attempted to say it's 1x, but wait a second. Our theorem insists that it's an orthonormal basis. So before we talk about basis, we should decide what our inner product is going to be. So what inner product are we going to use here? What will be our inner product between f of x and g of x? Which inner product are we thinking about? Well, we could just define it to be the dot product between the corresponding coordinate vectors, but like that wouldn't be a very interesting example. What's a more interesting inner product that we talked about for polynomials? Yeah, let's find the definite integral from, say, I don't know, 0 to 1 of f of x times g of x dx. So our adjoint is going to depend upon our choice of inner product, right? And so what is our goal? Let's just remind ourselves here what our goal is. Our goal is to find some map so that the inner product of d f of x with g of x should come out to be the same as f of x times whatever this adjoint is, g of x. So you're like, this is the definite integral between the derivative of f and g, and this is the definite integral between f and what? Like something to do with g, and it's not clear what that should be right now. And it's clearly not derivative, right? Like the definite integral of the derivative of f times g is not the same as the definite integral of f times derivative of g, right? That's not true. So like, what is this guy going to be? Well, that's our goal. But since that, here's our inner product. This, in fact, while it's a basis, is not an orthonormal basis. We want an orthonormal basis. So we can still have as our first vector the vector 1, but it's like, what's our second vector going to be? What's our second vector going to be? I think we did this before, didn't we? Do you remember what it was? And we can do it really fast. It should be something in the form a plus bx. And so it's like, okay, I want them to be orthogonal to each other. So I want the inner product, which is the definite integral from 0 to 1, of 1 times the other of a plus bx to come out to be 0, because I want them to be orthogonal. So when is that 0? Well, let's just calculate this. This is just going to be ax plus 1/2 bx squared, which when you plug in the bounds just gives you a plus 1/2 b. So like, what should our values of a and b be to give you 0? And you're like, well, it's going to be some constant. I don't know what the constant is. I guess I'll call it alpha, times something of the form 1 minus 2x. Some constant times this, right? I could just pick that, and it'll be orthogonal to 1, but it may not be normal. It may not have unit length. So now I'm going to pick my constant so this has unit length. So it's like, how do I pick my constant so this has unit length? Well, I dot it with itself, or I take the inner product of this with itself, which is the definite integral of this times itself. So alpha here, this times itself is 1 minus 4x plus 4x squared. And I want this to come out to be 1. Right, that's my goal. I want this to come out to equal, I guess I can put it here, 1. So what should this be so it equals 1? Well, let's solve it really fast. Oh, that should be alpha squared, right? Because I times him by himself. So alpha squared times, this gives you x, which is 1, minus 2x squared, which gives you minus 2, plus 4 thirds x cubed, so plus 4 thirds. So that gives you negative 1, so this becomes a third. So you get 1/3 alpha squared. It should be equal to 1. So 1/3 alpha squared is 1 when alpha squared is 3, which means alpha is the square root of 3. How about the negative square root of 3? Yeah, you could pick that instead if you want. So this should really be the square root of 3 minus 2 square roots of 3x. Or you could do the negative of that, that's fine. So now we have an orthonormal basis. 1 and the square root of 3 minus 2 square roots of 3x. And so let's figure out what this matrix D looks like. Well, this matrix D, the matrix corresponding to derivative, should just look like whatever the derivative does to the first guy, to 1, expressed in its coordinates, and whatever the matrix does to the second guy, whatever the derivative does to the second guy, square root of 3 minus 2 square roots of 3x, expressed in its coordinates. So what is the derivative of 1? Well, the derivative of 1 is, I guess I'll do it right down here. The derivative of 1 is just 0. So that's easy. That's just 0 copies of the first guy plus the second guy. Right? That's just 0 copies of v1 plus 0 copies of v2. So this first column is just going to be 0, 0. And what does the derivative do to your second basis element, to your v2? So what does the derivative do to square root of 3 minus 2 square root of 3x? Well, that's just negative 2 square roots of 3, which is exactly equal to negative 2 square roots of 3 times the first vector, copies of 1, and 0 copies of the second guy. So this just looks like minus 2 square root of 3, 0. I'm going to write it as a round bracket. Happy? So then, if I'm interested in the adjoint, then I know that the matrix corresponding to the adjoint should just be the conjugate transpose of the matrix corresponding to D. Since we're working over the real numbers, this is really just the transpose of that matrix. And so by my theorem, I now have that, so therefore, the matrix corresponding to the adjoint should just be the transpose of this matrix, which is just 0 minus 2 root 3, 0, 0. And now what we want to do is, now that we have the matrix, we want to take that back up. So now we have this matrix. I want to ask, what's the linear transformation that corresponds to this matrix? Right? So I have the matrix, and I want to know what linear transformation corresponds to that matrix. What does my D star do? And so one way to understand linear transformation is to just understand what does the linear transformation do to your basis elements, to V1 and V2. So let's just think. What does my linear transformation do to 1? Well, whatever my matrix does to 1. Whatever this matrix 0, so maybe let's write it down here. It's whatever this matrix 0 minus 2 root 3, 0, 0 does to the matrix, to the vector that corresponds to 1, which is 1, 0, because it's the first basis element. Well, that's going to spit out 0 copies of the first guy and minus 2 root 3 copies of the second. And that corresponds to what value? Well, it's just minus 2 root 3 copies of V2. So do your minus 2 root 3 times your V2, and you get negative 6 plus 12x. Is that right? Negative 6 plus 12x. Did I do that correctly? Think so? What does D star do to, well, let's just ask what it does to x. Then we'll be able to figure out what it does to anything of the form a plus bx. So we figured out what it did to 1, or in general, if there's a constant, you scale it by a constant. What does it do to x? Well, it's this matrix, 0 minus 2 root 3, 0, 0, times, what is x? How do I write x in terms of my basis vectors? Well, if I want to make the second guy x, I need to divide by negative 2 root 3. So it's like going to be negative 1 over 2 root 3 copies of the second guy. But if I divide by negative 1, 2 root 3, yes, I get an x here, but this first piece becomes a negative 1/2. So then how do I get rid of that negative 1/2? Well, I need to add a copy of 1/2. So I need to add 1/2 a copy of the first vector. So x is really the same thing in terms of coordinates as 1/2 and negative 1 over 2 root 3. And I feel like I made a terrible decision by trying to squeeze this in down here. But we'll keep going. So then what do we get? You multiply this out, and you just get 0 and 1/2 times this, negative root 3. Which is almost the same thing as above, but it's half of it. It's almost the same thing above, but it's minus 3 plus 4x. So here is what your adjoint map does to 1 and to x. Question? Did I mess up?
Negative 6.
What was that?
Maybe negative 3.
Oh, that's 6. Yes, half. Half of the guy above it. Thank you. Half of 12 is 6, not 4. Very good. Thank you. So what does this map do in general? Right? Like, I know what my derivative does. If I'm taking the derivative of some vector a plus bx, it's just going to spit out b, right? But what does the adjoint of the derivative do? Well, the adjoint of a plus bx is going to spit out, because it's linear, this is the same thing as just a copies of the adjoint acting on 1 plus b copies of the adjoint acting on x. And therefore, it's just going to be a copies of the guy on top minus b copies of the guy on bottom. A copies of minus 6 plus 12x plus b copies of minus 3 plus 6x, which gives you the same thing as minus 6a minus 3b. So minus 6a minus 3b plus 12x plus 6x. 12ax, so 12a plus 6bx. So that's what the adjoint map does. And you're like, that's a weird map. Yeah, you know, it's not the nicest of maps, but it works. This holds true. You know, you can go ahead and plug this in general. Like, you should probably do this exercise at some point, and convince yourself that if you plug this in, I don't know, just begin with two arbitrary guys. You know, convince yourself that if you're doing the antiderivative from 0 to 1 of the derivative of a plus bx times some c plus dx. Oh, dx is unfortunate notation. Oh well. Calculate that out. Right, this is just b times that, and show that you get the same thing as doing the definite integral from 0 to 1 of a plus bx times this map, described this way, the adjoint map acting on c plus dx. C plus dx. dx. Okay. This is the variable d times x. This is the differential. So a little bit confusing. Okay, and you can check that you actually do get the same thing in both of those. I did last night. It works, promise you. But we just showed by our theorem it's going to work. Okay. So the big story is, for matrices, the adjoint is just transpose, or complex numbers conjugate transpose. Same thing is true for finite dimensional vector spaces. You just move it down to a matrix, take its conjugate transpose, and then move it back up. And yeah, it's kind of a pain, but as long as you work with orthonormal basis, it all works out.